Okay, in this lecture we will introduce hypothesis testing. So the first thing here is just to look at variables, parameters, and statistics. This is just an overview of the kinds of variables and the parameters and statistics. Variables are things that can vary from one element to another, and those can either be qualitative, which we'll also call categorical. That's why I wrote that there. Qualitative, we're just putting things in a category. Quantitative, we're actually measuring how much of something or how many or something like that. Two quantitative would be, well, two quantitative variables like hours of training and productivity or something like that. Categorical or qualitative could be something like gender, whether or not you've completed a course. So yes or no, or we could put things in more categories like what color of eyes. For now, we'll look at proportions, which is just two categories, so yes, no, passed a course or not. Quantitative could be score on a test, number of people in the room. Parameters and statistics. Parameters are characteristics of an overall population. So for a categorical variable, we'll have the population proportion, and then statistics are characteristics of samples. So for a categorical variable, we'll have the sample proportion. So we'll use that p-hat sample proportion as an estimate or to test hypotheses about the parameter for the population proportion. For quantitative variables, the parameter is the population mean, mu, and we will estimate that with the sample mean, x bar. And for two quantitative variables, we'll have the correlation. The population correlation is rho, that's our population parameter. We would like to know about the parameter, but all we can have is information from the sample. So we'll have the sample correlation r. So a couple of things here. One, just a memory tip. Parameter and population both begin with the letter P, so parameters are characteristics of populations. Statistics and sample both begin with the letter S, so sample, statistics. Mark there is that except in a couple of cases where we do it for theoretical reasons, theory development, we won't calculate parameters. We're trying to estimate those or test hypotheses about them. That's what we would like to know about, but we don't have very frequently a census of the whole population. So we'll have to base our judgments on what we can calculate. And what we can calculate are statistics. In this case, the sample proportion, sample mean, sample correlation. Other statistics we will look at will mainly be based on these, like the difference between proportions in two groups. So we'll have, for the parameter, PA minus PB, proportion for categorical variable P hat A minus P hat B, and then for quantitative, mu A minus mu B for the parameter, and x bar A minus x bar B for the statistic. You can have difference between correlations, but we won't do that in this class. You can also have two qualitative variables. That one will be a little bit different in how we approach it, and I'll wait until we get there to cover that. A couple of things about hypotheses. First of all, they should be a priori, which means that you should state hypotheses before you collect any data. Would be, I'll say, unconscionable to collect the data and then formulate a hypothesis that goes with your data. Falsifiable, that means you have to, when you test a hypothesis, it has to be something that you can say is true or not. You have to be able to make to say it's not true. The null hypothesis is our HO. Basically what we're saying there is any difference that we observe from what we have in the null hypothesis. Let's say that we think the hypothesized mean is 70. One explanation for a difference, let's say we had x bar is 71. That's different than 70, but that could just be due to sampling error. Another thing about the null hypothesis, always have an equal sign in it. Then the alternative, or research hypothesis, now when we look at that difference between 71 and 70, now we say that's not just sampling error, there's some real effect. The score has changed. The overall logic of hypothesis testing. So when we're performing the test, when we're calculating probabilities, and you'll see some of those in just a minute, when we calculate those probabilities, we assume the null hypothesis is true. Gather some data, calculate the statistic, then we determine the likelihood of selecting the data that produce the statistic or some value more extreme. So we'll have a name for that. We'll call it the p-value. If the data are likely, if the p-value is high, then we'll conclude that the null hypothesis may be true. However, if they're unlikely, if the p-value is low, if HO is true, we would be unlikely to get these data. then we will reject HO and conclude that we have support for the alternative or research hypothesis. One of the things I'll go ahead and note here is that because of the nature of the errors that can be made and their probabilities, support for the null hypothesis and support for the alternative hypothesis aren't the same kind of thing. Basically, we almost really can't support the null hypothesis. All we can do is not reject it. For example, to give you, if we had that 71 and 70 and we failed to reject HO, we might say that the mean could be 70, but obviously it could be something else as well. It could be 71 or 72 or some other thing. So we can't really ever conclude that the null hypothesis is true, but we can, with a known probability of error, conclude that the alternative hypothesis is true. Again, that's something else that will come up again in some more slides here and throughout the course. So if you don't quite get it the first time, hang on. Might have to watch this video again, but may get to it later in this video and elsewhere as well. Okay, this again I hope is a little bit of review, but just to give you some example of some research questions and hypotheses. Looking at the new Walmart market on West Main. So one question we might want to know: has more than 60% of Russellville residents shopped at the market since it was opened a few months ago? HO is that we have any difference from 60 is just random error. So we'll say HOP is equal to 0.6. If it's more than 60, then we'll say that whatever we observe, let's say we observe P hat of 0.62, that might be enough to say that HO is unlikely to occur, therefore we would conclude that the P is greater than 0.6. Is the average time a shopper stays in the store less than 15 minutes? So if there's no effect, if no effect would be if the mean is equal to 15, that's our HO. Based on what we observe, do we get an X-bar sample mean enough less than mu, less than 15, to say that no, mu equal 15 is unlikely, and therefore we're going to conclude mu is less than 15. I'll just state it here for the linear relationship. HO rho, the population correlation, is equal to 0. 0 is no relationship. And then H1 or HA or HR, whichever you want to call it, is not equal to 0, that there is some 0 or non-zero correlation. You'll see that quite a bit too on the notation. The null hypothesis is always, in any book that I've seen, designated as H0. For the alternative hypothesis, it might be designated as H1, HA for alternative, and occasionally you can see it designated as HR, where R stands for research hypothesis. Okay, just to give you a little bit of a different way of looking at the logic of hypothesis testing, let's say that our HO is that we have a fair deck of cards, 52 cards, and if it's fair, overall, if you did this many times, or what would be the expected value if I dealt 20 cards, what you would expect is 10 of each, or at least close to 10 of each. Sample to sample, you're not always going to get exactly 10 black cards and 10 red cards, but on average, you ought to get somewhere close to that. So, if I dealt 20 cards and 12 of them were red, I think it's reasonable to say the null hypothesis could be true. Because if it were true, getting red isn't all that surprising. It's fairly likely to happen. And so those data are consistent with that. Of course, we can't accept that it's a fair deck because this is what I meant about that. Really can't support the null hypothesis because obviously you have 12 out of 20. Well, maybe 60% of the cards are in red, or 63 or something like that. At any rate, just back to the first part, we can't say that the null hypothesis is untrue. Therefore, let's play cards. Looks like we may have a fair deck of cards. We at least won't reject that out of hand. However, if I dealt you 20 cards and 19 of them are red, you should be suspicious about whether or not we have a fair deck of cards. So now the null hypothesis, given this data, the null hypothesis is unlikely to be true. And this is really what the p-value is if we had a fair deck, a 50-50, and we got 19 out of 20, it seems very unlikely that that 19 out of 20 came from a fair deck of cards. Okay, so yeah, this is a big slide. If you haven't seen the video is already about the binomial distribution. Also the short video I made talking about the online binomial calculator. This is one of those slides where you might want to pause and rewind from time to time. There's quite a bit on here. Well, first of all, on the left-hand side here, what I'm saying is on this side is that HO is that P is equal to 0.6. That is my null hypothesis. So I'm going to take a sample of size 20 from a population where I assume P is equal to 0.6. And so what I have on the left-hand side here is the binomial distribution for n equal to 20 and P equal to 0.6. When I go through the hypothesis testing procedure, I'm going to pick 20 items, pack and put this in the context of the 60% of shoppers have gone to the new Walmart market. Again, HO is no effect, P is equal to 0.6, so we have this probabilities distribution here. And when we test our hypothesis, there's always a chance that we're going to make an error. And we'll divide those into what's called type 1 and type 2 errors. A type 1 error is the likelihood that we reject HO incorrectly. And we can set that to a specific level. What I've done right now, usually a common level is 0.05, another common level is 0.01. So what I've done is I've looked over at the probabilities in this distribution table. So if HO is true, the likelihood that we would incorrectly reject, and I'm going to just pick a point that's where the probability is close to 0.05. It turns out that the probability of 16 or more, if you just add those up, you'll get at least close to, I think, 0.0509. If you did it using the cumulative portion of the table, you get almost the same thing, but you would do 1 minus 0.949 is 0.0510. If we're going to, I'm going to set as a rule, reject HO if I get 16 or more shoppers that have gone into the store. And if I get 16 or more, I'm going to then conclude that the research or alternative hypothesis is true. Sometimes I'll be right, sometimes I'll be wrong. Let's say I get 17. HO could be true, and I'll get 17.0123 of the time, or 17 or more. I'll add those up. Looks like 154, 1.0159 chance that I would get a value down here even if HO is true. But I still have to make some choice. I'm going to reject if it's greater than 16, and I'm going to say I'm willing to be wrong a little more than 5% of the time. So all the left-hand side here is the null hypothesis and the probability that we could make an incorrect decision. Of course, if it's true and we get anything that's 15 or less, then we will have made the correct decision. So that's one side. On the other side here, our HR is P greater than 0.6, or suppose is that the real P is 0.8. It's going to be unknown, but in fact, both of these will be unknown, but let's just assume that real P is 0.8. So a type 2 error occurs if we incorrectly fail to reject HO. We are going to fail to reject HO anytime we get X less than 16. So we will reject HO, or fail to reject HO up here. But the type 2 error is if this distribution, if the real distribution, the 0.08, is true, what's the likelihood that we would fail to reject HO? We're going to fail to reject at 15 or less, and we see 0.3704. So that then is the probability of a type 2 error. And then the power of the test, which is the likelihood of finding a true effect when it exists. So to find this true effect that it's greater than 0.6, if it really does exist, would be 1 minus that error. Probability of a type 2 error, 1 minus 0.3704 is 0.6296. Again, what I'll suggest to you right now is take a break, come back, rewind past this slide and give it another try, and also read the section in the textbook on that.